We've already learned about work and kinetic energy, and now we're going to put those two things together in what's called the work-kinetic energy theorem. The work-kinetic energy theorem says that the net work, or the total work done on an object, is equal to the change in kinetic energy of that object. There's two ways to calculate the net work. We can either say that the net work is equal to the sum of all of the work by all of the forces. So the work done by force number 1, which might be gravity, plus the work done by force number 2, which could be normal force or an applied force, plus the work done by any other force acting on our object. Sometimes there's only one force that does work. Sometimes there can be 3 or 4 forces that do work. Another way to calculate the net work is to use the equation for work, but instead of just plugging in any old force, I would plug in the net force times the displacement times the cosine of the angle between the net force and the displacement vectors. This is a very important theorem in physics, and it'll be very useful in some of the problems that we'll deal with. One very important comment I have to make is that every single problem that we do in this chapter must use a work or energy concept. You'll notice as we start with these problems that many of these problems can be solved in multiple ways. Be careful to make sure that you're only using work and energy concepts to solve them. Let's start with this example. Example number 5 talks about an 88-gram arrow being fired from a bow. The string on the bow exerts a force of 110 newtons, and it exerts that force over a distance of 78 centimeters. We want to know the speed of the arrow as it leaves the bow. Let's start by writing out what we know. We know mass is 88 grams. We know that force is 110 newtons. We know that the distance, which in our equation is going to be the displacement, is 78 centimeters. And one thing that we're not given is a number, but if we think about the situation, we know that the initial speed of our arrow is 0. In other words, when you're holding it right before you release it, that arrow isn't moving. After we write out everything we know, one of our first things we need to do is to convert units so that all of our units match. While it may not seem automatically right off the bat that all the units don't match, we talked about in class how newtons is kilograms meters per second squared. So this mass must be converted to kilograms, and this displacement must be converted to meters. Now we're ready to continue on. Based on the fact that I see in this problem a force, a displacement, and a velocity, I know that I'm going to use work-kinetic energy theorem to find the final velocity of the bow. That tells me that net work is equal to the change in kinetic energy. I'm going to go ahead and take the approach of adding together the work done by each individual force. So let's ask ourselves how many forces are acting on the arrow while it is in contact with the bow. Well, we know that there is a force of gravity acting on the arrow. We also know that there is a force from the bow acting on the arrow. Those are the only things that are touching this arrow at that point in time. Does the force of gravity do work? Well, let's think about that. The arrow is ideally moving horizontally, while the force of gravity is downward. So if I wanted to calculate the work done by the force of gravity, which is Fg delta x cosine theta, what angle would I have between the force vector and the displacement vector? If you said the angle is 90 degrees, you're correct. The cosine of 90 degrees is 0. So the work done by the force of gravity is 0, which means the force of the bow is the only thing doing work. Let's calculate how much work that bow does. That's the force of the bow, 110 newtons, times the displacement, 0.78 meters, times the cosine of the angle between the two. The bow is the only force causing this displacement. That means they have to be in the same direction, so the angle between the two of them is 0. When I multiply this out, I find out that the work done is 85.8 Newton meters. That has to be equal to the change in kinetic energy, because that's the only work being done. So the change in kinetic energy is 85.8 Newton meters. Change is always calculated by doing final minus initial. My object is not moving initially. One of the givens we wrote down was that V initial is 0. That tells me it has no kinetic energy initially. So the final kinetic energy is equal to 85.8 Newton meters. The equation for kinetic energy is 1/2 mv squared. And because it's final kinetic energy, this is final velocity squared. The last thing we need to do is solve for velocity. I'll do that by multiplying both sides by 2 and dividing both sides by mass. So I have V final squared equals 2 times 85.8 Newton meters divided by mass. And then to get final velocity all by itself, I'll take the square root of both sides, so that the final velocity, really final speed in this case because we don't know anything about direction, is the square root of 2 times 85.8 Newton meters divided by 0.088 kilograms. This gives us a final speed of 44.16 meters per second. Let's look at another example. In this one, we want to know how much work is required to stop an electron when it's moving at a speed of 1.9 times 10 to the 6th meters per second. Again, if you see a problem that has something to do with force and something to do with velocity, or something to do with work and velocity, that is an immediate hint that you'll be using the work-kinetic energy theorem. Let's write out what we know. We know mass is 9.11 times 10 to the negative 31st kilograms. It says we want to stop the electron. So final speed is 0, and it's initially moving at 1.9 times 10 to the 6th meters per second. Okay, so I know that the net work, which is what I'm looking for in this case, is equal to the change in kinetic energy, and change is always final minus initial. If we're stopping it, that means it's not moving, so the final kinetic energy is 0. So that means that the work that's required to stop this electron is equal to negative K initial, or negative 1/2 m V initial squared. I'll leave it to you to plug numbers in there. Pause the video, plug it all into your calculator, and then unpause for the correct answer. Hopefully, you got 1.644 times 10 to the negative 18th joules. If you didn't get this value, then go back and check your work. This seems like a very small amount of energy, But if you think about it, an electron is a very, very small particle. So even though it's moving extremely fast, it doesn't take much work to get that. Also, this work should be negative. That's because I'm taking energy away from the electron, not giving energy to the electron. This last problem here talks about accelerating a car from rest. We know that there are two forces acting on it. And we want to know how far the car must travel for its speed to reach 2 meters per second. This problem I would like you to try on your own. Make sure that you show your work in your notes.